All right, so why don't we start with number 6, since it was one of the most requested. Um, and you're asked to find the force on a particle, and here's your variable force graph. And you're asked, so we know right away that it's the area under the graph that we're looking at. So for A, I just did a bigger version. They want me to do it up to 6. So that's going to be here. And I'm just going to kind of subdivide that graph into 2 segments so I have 2 regular shapes. So I'm just going to do the area there for 0 to 6. And I do 1/2 base times height plus the base height of the next section, right? And need to go further? You good? For B, you're going to have positive work for the first part and negative for the second. Did you do that?
Yeah, so you use the first part minus the second.
Yeah.
It took us
Okay.
What did you get? 6.
I got 21.
Oh, which so I
Maybe. Yeah, or 1.25 or something like that. This one I would say is 2, yeah.
Yeah. Okay.
Yeah, so it's not a symmetric trapezoidal type shape. Trapezoidal? Yeah, trapezoidal. So that's it was probably just that.
Okay, for the second one,
Yeah.
you add just the total areas and you subtract the lower one.
Lower one is a negative area.
So
So you're adding energy to the system by the positive work, taking energy away. So the net work is going to be the top minus the bottom. All right, so 8 was the next selected. Are people ready to talk about 8? Or yeah? Please, Liz is right. All right. So you have the heavy chain outward lab here, and I have 1.8 meters up here, so 1.2 meters hanging down here, and over the edge, once the chain is moving, friction is so small that it can be neglected, so it does no work on it. How much work is performed on the chain by the force of gravity as the chain falls from this point until the entire chain has left the scaffold. So I'm going to also draw the final situation here, which would be like that, right? And so what I'm looking at, they told me the linear weight density. That was nice of them, rather than just the linear density. So we're looking at really the work that's being done is taking the potential energy and changing it into kinetic, right? And so we want to look at, if we think about this chain, we can think about it as a whole. I'm going to think about it in 2 sections. I'm going to do the 1.2 and I'm going to do the 1.8 separately. I know that they're connected and that the work is done on both, but I think it'll be an easier approach. So I'm going to kind of divide mine here. All right, and this will be the bottom part here. Maybe I'll go over in green. Will be this hanging section, and the top part will be that. So, for the top part, the center of mass has moved down to this point, which is 0.9 meters down. Right? And for the bottom portion, the center of mass moved here, but it started here. So it's 0.6 and 0.6, so it should have moved 1.8 meters down. And it started off 0.6 below the level and moved down till it's 0.6 below the final, above the final. So that'd be a movement of 1.8. Yes? All right. So the work that's done on here then is going into taking this potential energy and converting it into kinetic. So I'm going to do kind of the work is the change in the potential energy for each of the segments. And so that's going to be mg delta H. So I'm going to have the weight of, and I've got my linear density, which means that times my length will give me, linear weight density, excuse me, that times the length will give me the weight of each of these segments. So if I do my 35 newtons per meter, and I multiply that by my 1.2 meters, that's the weight of the green section, and that changes height 1.8 meters. That's the weight of the green. The work of the blue would still be my 35 newton meters. It only moves 0.9 meters though. Oops, sorry. I got ahead of myself. Its length is 1.8 meters. And it moves 0.9 meters. Those summed up should give me the total work done here. Let's see. Oops. No. Tutorial shows you the author's way, which may not be the right way, or the best way. A number of children playing in two sleds at a smooth level snow-covered playground. Ask the tires to attend inside the configuration shown below. Give the fastest run. Betty and Carl. Let's see, Carl. I'm saying Carl's up here, right? 231 newtons. 20 degrees. 200 newtons. 23.27 degrees. So the work net equals 0. You guys remember from last year, or you're reading the work kinetic energy theorem, that the net work done on something is the change in the kinetic energy? Did you have that last year, or you've seen it? Yeah, hopefully it's a bobblehead. Yep. Work net is the change in the kinetic energy. So that means in this case, as much work is done by Carl and Betty as is taken away by David sitting there. All right. So determine the following. Of course, I didn't bring the following over. The amount of work done by Betty and Carl, the work done by the tension on the connecting rope to the leading sled, the work done by the tension on the connecting rope to the trailing sled. So, all of these, the first two are going to add up to being C and being D. Yeah. Sorry? So, let's go through and figure out. Oh, it's pretty straight. Hopefully, pretty straightforward. We're doing W equals F dot delta D. And so for Carl, the work of Carl is going to be 231 newtons. And then, because it's the dot product, we have the cosine. So I'm going to think of that as cosine 20 degrees times 20 meters. Oops, 20 degrees. Because that's how far the sled moves. Work by Betty will be her 200 newtons. Cosine 23.27 degrees, and then 20 meters. That's a 20. I'd written it 2 hastily and then added to 0. Better? And you're welcome. Because the network is 0, whatever work they're doing on that first sled has to be counterbalanced by the work the tension is doing, and hence forward and backwards that whole way there. And since they don't tell us anything else, when they say smooth, level, snow-covered playground, they're saying that the energy isn't going into friction by the smooth, it isn't going into gravitational potential because of it's level. I'm assuming the rope is inextendable, so it should all come out. Yay! Anyone try it? Did it work?
Also,
all right, so by request, 13C just became valued at what I think it's worth. I was told only 2 is needed, really.
sure, let's do A and B too.
You need A and B. You need to enter A and B.
Yeah.
Yeah.
Why don't I go through C, and then those people that have already done A and B can stop paying attention, and we'll talk about A and B. That make sense? Okay. So this is one of my favorite ones because people forget that while the spring compresses, gravitational potential energy is still being changed into elastic potential energy. And so I like to show it best through a diagram where we've got a big old Mongo spring and the elevator hits it, and it's going to go down. We're going to call this delta H. It'll compress it down to there. And so this, I think, is modeled best through kind of a bar graph where we have KE, PE grav, PE spring, And then you have afterwards the same 3. All right. So when it hits, a lot of kinetic energy. When it finally stops, how much kinetic energy does it have? 0. It also has a certain amount of gravitational energy. Because I'm going to say that this red line down the bottom where it stops is 0 for the gravitational potential energy. So what that means, since the energy has to be conserved, we don't have any spring energy yet, but afterwards, both of these have to combine and that's how much spring energy we end up having to have. So a lot of people will take and say, oh, okay, well they have the speed, so I must have kinetic energy at the top of the spring, and that's going to be stored as potential energy in the spring, or converted to potential energy as they change the position of the spring. Yay! Okay, that's not right, because they forget about that red column there, also having to go in there. So the way I would set it up, energy at, call that as A and B. Energy at A has to equal energy at B. Energy at A is kinetic energy, and U grav, that has to equal U spring at B. So this is going to be 1/2 mass speed squared plus mg delta h, and this is going to be 1/2 k delta h squared. And they want to know, I think, delta h, right? So you know m, you know g, you know v because you did part B, and you know k. And the only thing you don't know is delta h. It's a quadratic, but that's not a problem, right? Yeah. So to do A, I would suggest the amount of work done by gravity is the change in the kinetic energy, in the potential energy. So that would be U grav, which would equal the mg, and then the h here, and the h is your 22 meters. And then for part B, the delta U, I should put a delta. Delta U grav goes to kinetic energy, which is of course 1/2 m speed squared. Oh.